questions. So I've put around some self-assessment questions. Okay. Now these self-assessment questions, you're not expected to send their answers back, but you're welcome to start a discussion or send your queries and problems along this. You can directly send it to me, and our discussions will start. Also, these lectures are for 3 hours now. Okay? So 2 hours will be the lecture, and 1 hour will be the discussion. Okay? So it keeps you, so you can have enough opportunity to have your doubts clear. Now, then what are these self-assessment questions? Well, they are giving you a kind of a skeleton. If you have the answers to these questions, you know the material pretty well. Sure. Okay? And you should be able to produce these answers by yourself. Yes, while learning, you can take up a book, you can use these lectures, and so on. But at the end of the day, you must have answers to those questions. So, is it clear what? You will see that the self-assessment questions are in 3 levels. Okay, level 1, level 2, level 3. Well, level 3 is, it's beyond this. It's not examinable, as I've already said. Okay, but understanding level 3 will give you a real good grip of the picture. Okay. So now let's look into what the material of today's lecture set in. Now, in all of mathematics, after Cantor, sets turned out, or now sets are the only carriers of mathematical thought. We express everything in terms of sets. And why this is so? The reason is very, very simple. We do not want any kind of a dual meaning to any statement that we make. So a statement that I make is going to be understood by anyone who understands that language. And in the same way that I wanted to mean it, so there is no double meaning. Okay? So everybody understands it in the same way. Okay? So that makes our life much more simple. So, and set theory is the first step towards that. Okay? Now, how do we understand sets? So what shall be sets for us? Well, sets, sets, they don't hide. Oh, okay. No. Okay, let's try. Sets, we shall not try to define it. Okay? We will accept it. We will understand how to recognize it. Okay? So we know, so roughly speaking, it is a collection of well-defined objects. Okay? So let me say that we will understand it to be a collection of Okay? Now, what do I mean by this? Given any object, we would be able to say whether that is considered in that set or not.
Sure.
Immediately. Okay? So, we would either be able to write down all the objects which are there in that set, or we would give a property. Okay? We would give a property which every one of those elements of those objects have, and no other object has. Okay? So, whenever that property is satisfied, that is considered in that set. Whenever it is not in that set, right? So, we will use this symbol. The symbol shall mean that here, what is we are late.
I saw you dancing. I was there. I didn't know you. The venue was changed. Yeah, we were told 105. I've been here since 8 o'clock. I saw you downstairs. I never knew you anymore.
Perfect.
Yeah.
So this is the set. This is an element. And this is a special relationship. It is called the belongs to relationship. Okay? So this statement means that the element X belongs to the element X belongs to or is a member of the set A. And when I write this means that, so this is a statement, X belongs to A is a statement, right? When I write this, it means that this is false. And by that I obviously mean that X is not an element of the set A, and or it is not a member of the set. Okay? Now, how do we so about listing? So for instance, we can write this set A by listing all the elements. Say I'm speaking about these small letters. Okay? Or so this is often called listing all the elements. Or we write a property. Let's say alpha, so that alpha is a small letter of the English alphabet. Okay? So the property is alpha is a small letter of the English alphabet. This is the property which is common to each one of these elements and which anything beyond this doesn't have. So if you take B, this is not a small letter of the English alphabet, so it is not there. Okay? So just like that, so there are two ways. Now this often this listing procedure works if there are 10, 20, finitely many elements. If there are many elements, Well, even for 10 billion elements, you cannot list all of them in your paper, but you can possibly do it on a computer, right? But the second one is a much clever way of doing it. Instead of listing it, okay, it's a much clever way of doing it, to get it by properties. So, for instance, here is a very nice some special sets. So here is a very nice set. It consists of all those elements X it's a property, right? Obviously, I know that there cannot be anything which is not equal to itself. Okay? We call this the empty set and we denote it by this symbol. This is the empty set. Sorry, this is the empty set. It has no elements. No. This is empty set. It's equal to the empty set. Obviously, I didn't say, I tell it just now. Just let me give some examples first. So, here is another set. So here is the set which contains of one and only one element, which is the empty set. Okay? You see, I can carry on from here, making more and more sets. There's another set which has two elements now. Now comes the question, why two elements? Well, because empty set has no elements and this one has exactly one element. Okay? So this empty set is obviously equal to the empty set, so it is not an element of this. Okay? So these are definitely two distinct sets. Okay? And so it's a two element set. Okay? Now observe, I can carry on with this process. It's a game. And so on. The game carries on. Okay? So you see, it has three elements. One is the empty set. One is the set which contains only one element, that's the empty set. And the third one is the set which contains two elements, the empty set and this one. Okay? So this set has three elements. Okay? Alright? Okay, if you carry on with the mathematics, you will see that this is indeed the starting point. This is how, going from here, using the axioms of set theory, we build all our sets. Okay? But that's a much later stage. Okay, now there came up the issue of equality of two sets. Okay? So this is the clue. So when are two sets equal? Since I said that a set is completely given by its property, its defining property. Okay? It's a bag, right? When are two bags same? When they have the same things. Right? That's the most natural thing. Okay? So, two sets are equal so this is the definition. If and only if both the sets have the same elements so that means, well, this is in words, as I said, everything should be in terms of this language, so it means, that is, if X belongs to A, this implies that X belongs to B, and both of them, right? So whenever X is an element of A, it is an element of B, and whenever something is an element of B, it is an element of A. So this is the way of saying, obvious way of saying that two sets are equal. Okay? And this is often shortened in this, we will often write this in this way. This is often shortened as X belongs to A if and only if we write this double implication means yes, if and only if, or one from one in the other false. Okay? So over here there is a special case. We say, okay, before I go that, so over here it is clear that, so therefore yeah? Okay? And because, why is this true? Y belongs to this one if and only if Y is equal to X and Y belongs to this if and only Y is equal to X or Y is equal to X, but saying this is the same thing as saying Y is equal to X, right? So this is the same thing as saying right? So what does it say? It says, furthermore, that you need not repeat the elements of a set. It doesn't change the set. Okay? Writing it once or twice doesn't matter. Okay? So that's why when we list the element once. Once if it is there, it is there. You don't have to list it 10 times to say it is there.
But even if you list it 10 times, though, it's not illegal.
It's not illegal. It's not illegal, but you're just wasting your time. Right? Okay? Alright. Now, if both of them occur, then we say that it is equal, right? Okay. if one of them occurs, that's the scenario of something called a subset. So A is a subset of B. We write it like this. So this means X belongs to A implies X belongs to B. Okay? So A is equal to B if only if what I wrote the definition yeah? A is a subset of B means whenever I take something from A, it is already in B. And B is a subset of A means when I take something from B, it is already in A. So whenever both of them happens, I know that means A is equal to B. Okay? So here is another route of showing A equals B. So whenever you have such set theoretic equalities, the way to establish would be you show both of them. Okay? So that's the computational route. You show, if you take something from A, it is also in B, so A is a subset of B, and you show B is a subset of A. Yes?
So it's not necessary to write that if A equals to B, the statement that X is an element of A only if X is an element of B.
That's exactly the same thing that I wrote. If you see, this part is now under that subset relationship, saying this. And this part, under that subset relationship, is telling me this.
So if I may say, that we have two conditions now. If A equals to B means one, if both the sets have the same element, and if A is an element of B and B is an element of A.
Firstly, having same elements is rephrased in this way. Okay? Now, this statement, X belongs to A, implies X belongs to B, has been given another form by saying A is a subset of B. Oops, what happened? One minute. Yeah. So this has been given the form A is a subset of B. And this statement has been given a form B is a subset of A. Okay? So there are no more two conditions. I'm saying it's the same thing.
Okay.
Alright? So computationally, it seems simple to look like this, but it is not at all anything new. It was already there. Yeah, except that I have said it in terms of nice relation. Okay? Now, over here, let me emphasize, as an example, here is a nice example. The empty set is a subset of every set. How do I prove this? Okay? So how do I prove this? So what do I have to show? So I have to show if I take an element from X, then it means right? Right? But what was this empty set? Empty set is the collection of all those elements so that that is not equal to itself. Right? So that means how the hell do I prove this? Take an element. This is where our basic logic comes to our rescue. So that's why I am doing this also. So this is a basic fact of our logic. And what is this? Well, firstly, as I said, you can make statements. Okay? So x belongs to A is a statement. X equal to Y is another statement. Okay? We have already built many other statements. So if alpha was a statement, so x belongs to A, beta was a statement, x belongs to B, then we have made this statement alpha and beta, which means x belongs to A and x belongs to B. That's the third statement. Right? Here's the fourth statement. X belongs to A or x belongs to B. Okay? Similarly, x belongs to A implies x belongs to B is yet another statement. Now, a statement can either be true or false. Okay? Good. Now, how does a statement which is of the form, say, alpha is a statement and beta is a statement. So, when does this statement, alpha or beta, is true? Well, I know. If either alpha or beta is true, this is true, right? So, this is true. Even if either alpha or beta is true. Now, how is this statement? Alpha and beta. When is this true?
Alpha and
Both
beta.
is true. Okay? If and only if both now, yes.
So the first statement implies that at least one should be true. So even if both of them are true, it's still fine.
Yes, it's still fine. It can be false when both of them are false. It's quite natural, right?
But
It's quite
at least one.
yes, if at least once. Now, about this one, this one is a notorious one. There are many ways of making this seem true, but the best is this. Let me tell you, this is a notorious one. And